Okay. Hi, everybody. Welcome to INSA. Welcome to PAO 2022. So before we get started with presentations this morning, I just want to say a couple of words, just to give you an overview of the program of today. So just to begin, I want to say thank you to INSA for allowing us to actually organize this here. They're letting us use the building and the rooms and everything, which is pretty nice. PAO is co-organized by INSA, INRIA, and GRAME. I think streaming is working, Tong. Very cool. So PAO is organized by GRAME, INRIA, and INSA. So just to sort of give you some background around that, traditionally, GRAME was organizing PAO for the past couple of years, and GRAME actually started PAO. And recently, we created a new research team, which is actually based here at INSA Lyon. It's called the Emerald team. And that team brings researchers from INRIA, from INSA, and from GRAME. And so this is why this year, PAO is actually organized by these three entities. Okay. So what's the program for today? So we're going to start this morning at 9:30 with the first oral presentation. So in the morning, we're going to have oral presentations, and in the afternoon, we're going to have workshops. Okay. So the first session will run until 11 a.m. At that time, we're going to have a coffee break, and at 11:30, we're going to resume, and we're going to have sessions until 1 p.m. I know it's pretty late, but that's kind of the only way we could do this. And we're going to have a lunch break at 1 p.m. Okay, so lunch break is going to last for an hour and a half. Okay, so we're going to resume at 2:30. I don't know if you noticed, but there are very few bars, restaurants, or stuff like this on campus. So if you want to get lunch, you're probably going to have to actually get out of campus, okay? So if you're presenting at PAO, your lunch is already taken care of, we're going to eat together. But for those of you who are just attending the conference, you're going to have probably to leave campus to get some food. If you scroll down to the bottom of this page, there is a bunch of suggestions for places where you can actually get food. There's the Ninkazi, there's the Universe Cafe, and there's the Atelier Salengro, which is a bakery, and they make very nice sandwiches. Okay, so those are our suggestions. Okay, but if you find something else, you can go somewhere else, of course. Okay, so this is just to give you an overview of this. Okay, and then in the afternoon, we're going to have workshops. Okay, so one thing that I want to insist on is that starting at 4:30, we're going to have two parallel sessions. Okay, so there is going to be one session which is going to take place here. Okay, and that's the session that you see here. So fast programming on FPGAs for high performance real-time audio signal processing and interactive audio and haptics on Bella. Okay. And then in parallel with that, there's going to be another session which will take place in the room that you saw in the hall of the venue. It's the room with the chairs with different colors. Okay, you really can't miss it. Okay, so it means that at 4:30, you're going to have to choose between this track or this track. Okay? So this track here is recorded and is live streamed. This one is not, okay, so for those of you who are actually listening to us remotely, you're not going to be able to follow this one, okay. Another thing that you should know is that there are actually installations in the building and demos. They're not really going to be ready in the morning, so you probably want to check them more in the afternoon, okay? And they're upstairs, so there is a staircase in the entrance of the building. If you go upstairs, there is going to be these three demos. One is the Spatbox by Pierre Lecomte, and these two are from our team here, and so they're just demos, so you walk in the room and then you try to use the system, and mostly it's for spatial audio, okay? We said it would start at 9. You know, some of them are already working, but you probably want to go in the afternoon, okay? Because not all of them are working for now. Okay, so yes. Okay, one more thing that I want to say, again, like for the thank you thing and everything, you know, is that we sort of co-organized this with Stéphane, who's here in the front. I'm sure most of you know him from GitHub or Slack or various mailing lists, you know, like, because he's kind of virtual figure in the community, and so here he is. Yeah, and I want to say thank to Tanguy too. Like, Tanguy is the head of the Emerald team, and he was a good facilitator for organizing this event. And I want to thank you all for being here. Thank all the participants, and and thank all the presenters. Another person that I wanted to thank is Yann Orlare, who's not here today because he has COVID-19. And so he's on the way out, and he's doing fine so far, right? And so yeah, Jan, you know, is the father of Faust, and he's the one who actually started POW. And so you know, Jan was going to be here today, but unfortunately he's sick, so he's not here. Anyway, do you have any questions, or should be pretty straightforward? Okay, great. So we're going to start with the first talk. The first talk is going to be by Loïc Alexandre on feedback acoustic noise control with Faust on FPGA, application to noise reduction in headphones. So Loïc, please come here. T'as du son?
J'ai pas de son.
T'as pas de son.
Bon. Non, je peux prendre peut-être l'USB-C direct.
Tiens, faut que tu te mettes ça quelque part. Je vais te l'accrocher parce que c'est un peu la merde à faire. Enfin, si j'y arrive. C'est pas un pull très pratique.
I guess everything is working. Okay, so thank you, Romain, and the organizing team for POW today. So good morning, everyone. My name is Loïc Alexandre. I'm a PhD student at the Laboratory of Fluid Mechanics and Acoustics in Lyon. And today I will be presenting the study we've carried out with my supervisors, Pierre Lecomte and Marie-Annie Galland, with the help of Maxime Popov, present here today from the City Lab, from here. So the study focuses on feedback active noise control using Faust on a FPGA platform with an application to noise reduction in headphones. So before I start explaining the principle of feedback active noise control and show you how we used it, I want to give you a little bit of context for you to understand. So this study and actually my PhD are part of the FAST project, which is a national research project gathering the GRAME, the City Lab, and the LMFA, my laboratory. And in the context of this project, the City Lab and the GRAME developed a toolchain called the Cifala toolchain, and it allows us to compile a Faust code in order to use it on the FPGA platform. So the idea is to use this Cifala toolchain for a practical application and actually with some educational interest. Just for you to know, Maxime will be presenting their work later this morning, so you will be able to see his presentation. So, as I was saying, there were some educational interests because actually the laboratory, the LMFA, is on the campus of École Centrale de Lyon. And the school uses the installations from the lab for some practical works. And one of them focuses on feedback active noise control in headphones. The thing is that currently, at least until the past year, they were using a quite old analog filter with fixed parameters, so it was not really flexible for the students to change them and see what's happening, the result in real time. So the idea is to use Faust, the Cifala toolchain, and the FPGA to kind of upgrade this experimental bench. Okay, so now that you have the context, I'm going to explain a little bit the principle of feedback active noise control and show you how we used it with FOST. Of course, nowadays the headphones with active noise cancelling, it's pretty known and easy to find. Usually the idea is to cancel, to attenuate a disturbing noise, for example here the noise from the aircraft. But when a company develops a headphone, usually they are able to optimize everything in this particular headphone. In our case, the idea is more to transform a passive headphone into an active one, with the idea that it has to be academic so the student can understand the principle. So since we cannot use the students as guinea pigs, we use the dummy head, the one you saw just on the picture before. And it has two microphones located simulating the eardrums of the listener. And for the control microphone, which in the case of a company headphone, it is located at the optimal position. In our case, it is an external microphone placed inside the ear, just to be able to change the headphone, replace the passive headphone. Okay. So taking this setup into account, we can imagine this scheme with the idea of reducing the pressure from a primary source at the eardrum microphone. So to do so, we need to introduce a secondary source, which in this case is the loudspeaker from the headphone, and the control microphone placed close enough to the eardrum microphone so that if the pressure is reduced at the control microphone, we assume it is also at the eardrum microphone. The question now is, what is the signal feeding the secondary source, the loudspeaker from the headphone? Well, to process this signal, we need to introduce the feedback loop composed of an amplifier with pure gain, not depending on the frequency, the control filter, and we'll see in a little bit what it looks like, and finally the transfer function between the headphone loudspeaker and the control microphone, which is called B here. Okay, taking this into account, we find that the total pressure at the control microphone is now equal to the pressure from the primary noise plus the total pressure itself going through the feedback loop. With this expression, we get this ratio that we actually want to minimize in order to reduce the pressure. And to do so, the only thing we can act on is the frequency response 8 dB. And the thing is that there is an unstable case when 8 dB is equal to 1 because of the division by 0. So in summary, what we want to do is to increase the modulus of 8 dB, but not for the frequencies where the phase is equal to 0, because then we can have the unstable case. Okay, maybe to make it more clear, we can see a practical case. So this is a measurement made from the experimental bench. And you see that in this case, it's just GB, so there is no filter, control filter. And the amplitude is in decibels here, so the instability will occur when the amplitude is equal to 0, not 1. You see on the phase response that the frequency, well, the phase crosses 0 at the frequency 5,169 Hertz. The thing is that at this frequency, the amplitude is almost the maximum amplitude of the frequency response, which means that normally when we increase the gain to actually apply some noise reduction, in this case, no attenuation will happen before the instability occurs. And in practice, the instability, it is the audio feedback, a really high annoying pitch. So in this case, we actually cannot have noise reduction. So this is why we need to introduce the control filter. But before designing the filter, we need to answer the question, what actually do we want to do physically? Well, since the headphone itself, the material will help attenuate the sound in the middle and high frequency, we want to focus the active noise control in the low frequency band. So here we actually focus between 50 and 1 kilohertz. So the filter should amplify the amplitude in the low frequency, but without changing too much the phase response, because we don't want the unstable frequency to shift inside the frequency region of interest. So one option to do that is a backward filter designed using two complex conjugate poles and two complex conjugate zeros. And you see on the right hand side that we focus on two parameters, the frequencies and the damping factors of the poles and zeros. So on the left hand side you see that the filter is actually doing what we want, amplifying the low frequency band, but the phase response is equal to 0 outside of the frequency range of interest, 50 Hz, 1 kHz. Okay, so this is great. If we introduce this control filter inside the feedback loop, we obtain now this result. You see that the unstable frequency is more or less the same as before, 2 Hz higher actually. But now the amplitude at this unstable frequency is not the maximum anymore. We have an increase, a peak in the low frequency, which actually comes from the control filter we just introduced. So this gain margin we have is actually the attenuation we'll get when increasing the gain. The low frequency will be amplified, but before we get instability, we will have attenuation happening. Okay, so this is great. It is what we can do currently in the experimental and the practical work. But the thing is that the student cannot change the parameters in real time and see what is the results, is it better or not for the noise reduction. So this is why we introduced the incredible FOST and the FPGA. Basically what we did is write a simple script. We define the frequencies and poles of the filter. Then we get the coefficients, the analog coefficients from it. And the TF2S function is doing the bilinear transform in order to get the digital filter. Of course, with digital filtering comes the latency. With the FPGA, we are using a sample rate of 192 kHz. We get a latency of 80 microseconds. And you might have noticed that the frequencies and damping factors are defined using sliders. This is just to get the graphical user interface for the students to actually change the parameters. Okay, so if we take the same example as before, a single backward filter, really similar to the analog one, but this one is digital, still doing the amplification in the low frequency, but you see on the phase response that now we have a slope, and this slope corresponds to the 80 microseconds of latency. So now if we introduce this first digital filter inside the feedback loop, we see that the unstable frequency is shifted to 3000 Hz more or less, which is lower than the previous one. But in this case, there is a particular and interesting phenomenon, is that for this frequency response, which corresponds to one position of the headphone and one position of the microphone, the control microphone. Well, in this case, shifting the frequency, for this new unstable frequency, the amplitude is actually lower, which means that now we have a bigger gain margin. So normally we'll be able to even increase even more the gain and obtain a better noise reduction. So we will see in a little bit if it is true. But what is really great with FOST and the FPGA is that it is really easy to change the configuration of filter. In this case, we can set two backward filters in series. The idea of this is just to broaden a little bit the frequency range of attenuation. And you see on the amplitude that it is still doing the same, amplifying the low frequency, but here in a larger frequency band. And of course, on the phase response, we still have the slope because of the latency, which is the same in this case. Now, if we introduce this new digital filter inside the loop, we see that the frequency of unstable frequency is again shifted a little bit, but still the amplitude is even lower than the previous case. And we still have this peak in the low frequency, which will help doing the noise reduction. Okay, so now that I showed you some cases, we can see actually what are the results and do we obtain a noise reduction. This is the noise reduction for the two single biquad filters. What we do basically in the measurement, we take the case without feedback loops, so without active noise control. We do the measurements at the eardrum microphone, and then we do the exact same measurement using as a primary noise an external loudspeaker. So we do the exact same measurement, but using the feedback loop and the active noise control. And what you see on the left-hand side is just the ratio of both measurements. So you see that for both cases, we have noise reduction on a quite reduced frequency band, but it is a bit higher for the digital filter, and it is what I said before, the margin, the gain margin is better, so we actually get a higher noise reduction. But what is more interested in our case is when we want to broaden a little bit the frequency range of attenuation. With the series of two biquad filter, we get higher noise reduction and broaden frequency range. Okay, so just to conclude, using FAUST, the CFALA toolchain, and the FPGA, we are able to get noise reduction to actually match what we would have with analog filter, and even have a better result up to 20 decibels. But the real interesting thing with the FAUST and the FPGA is the fact that we're able to change the parameters, to change the design of the filters in real time and really easily using FAUST. Of course, with the digital filtering, the drawback is the latency, but we've seen that depending on the case, on actually the position of the headphones and the control microphone, it can be limiting the frequency range of noise reduction. Talking about the position of the headphones and the case, we could actually think about an automatic adjustment of the filter, the parameters, in order to get a noise reduction and avoid the unstable frequency for any case. We could also use the latency. You saw that adding latency was actually better for the noise reduction. We could imagine adding some delay to actually get a better result. And I guess we cannot chain an infinity of biquad filters. But actually, a student already started to work on it during an internship. And you see on this picture that the FPGA is not anymore like a mess on the table. So this is a 3D model made by Maxime Popov, present here today. So yes, there are still a lot of work, lot of future work we can imagine. But since in our case, we're not looking for a company and making a active noise cancelling headphone, this is just for academic purposes. Thank you for your attention. If you have questions, I'm happy to answer them.
Questions?
Yeah.
You said the latency is about 50 microseconds?
80, yes.
18?
80.
Wow. 80? Okay.
Yeah.
Do you think it would be better if it would be lower? Do you think you could get better results with lower latency depending on the situation in general?
Yes.
Or is it just you were lucky in that case and it actually helped you?
Yes, I was lucky in that case because it was not limiting too much the frequency range of frequency. It was actually helping having a broadened frequency range. But yeah, in general, it is better having the lowest latency possible. This is why normally we use analog filter, because then we could imagine, okay, if we actually want to shift the unstable frequency, we could do it with an extra delay. It is better to be able to do everything and add some extra delay than having to be limited by the latency at the principle. Mm-hmm.
Thank you. Other questions?
I just want to say, for those of you who are watching us online, you can also ask questions through the chat, and we can ask them to the presenter. So if you have questions, feel free to ask them directly in the chat. So, yeah. Other questions in the room? Yeah.
I was just wondering about how this would work if it went into commercial production with the FPGA. Would you anticipate embedding this on an FPGA and headphones, or would you put it on an ASIC or something?
Yeah. I guess some headphones already use FPGA in their company headphones. But yes, of course, you have to reduce the size of the FPGA and add a lot of security filters, because it's really easy actually to get this unstable frequency. So you wouldn't want this to happen for like customers. So you have to add some security filters, and also right now it is just the noise, the external noise is just a noise, and we reduce this noise. But in the real case, there is also some music playing. So I'm sure in this case, the spectrum of the music would change a little bit, adding this active noise control. And maybe you've heard this when you put some active noise cancelling headphones. Sometimes you kind of hear another noise in the background. It comes from this feedback loop. But yes, in this case, we will have to add some other filters to be sure it works for music and in a real case scenario. Mm-hmm.
Thanks.
Still no questions on the chat? Okay, well, thank you, Loïc.
You're welcome.
So our next presenter is going to be Fernando Lopez Lescano, who's visiting us from Stanford University in the United States. And he's wearing Ping, the penguin. Okay, so we're going to have to stick to the schedule, so we're going to have to wait until 10 for those of us who are watching the conference remotely, so that it makes sense, so we'll probably have like 10 or 5 minutes, so if you want to go get a coffee, if you didn't have time to get one or whatever, feel free to do it, but the next presentation, next talk is going to be at 10, so thank you.
Should I start?
30 seconds.
Okay. Okay, so thanks for being here, and thank you to Omen and everyone for the opportunity to present this here. So I'm Fernando Lopez Lescano. I work at Stanford University, and I'm going to be talking about what happened during the pandemic to us, in a sense. And it's not just me. You should add all these names to the main core group that has been doing this. So before this started, we were having concerts without masks everywhere, happy. We had classes where we went in person without masks and learn about things. We had collaborations where we were able to do music without masks, and then you know what happened. So right after we went into lockdown in California and also in Germany. Right after Henrik von Koller, who's at TU Berlin, asked Chris Chafe, COVID is having some effects. So he was thinking about a series of streaming concerts, right? So Henrik talked to Chris Chafe, who's the director of CARM at Stanford. Chris talked to Juan Parra, who is in Europe, to Konstantin Basica, to myself. Henrik talked to Klaus, and we decided to do something, and the location is 3 of us in California, 2 in Berlin, and 1 in Ghent, Belgium. So geographically dispersed. At the very beginning, we said, how are we going to do this? So the audio exchange between performers is going to be using Jacktrip. So I'm not going to talk in detail about Jacktrip, but we'll talk about it a little bit. The video part, because we also wanted this presence to be visual, we started using Zoom, as probably everybody here, and eventually we switched to a different combination of Jitsi, which is an open source version of something similar to Zoom, and OBS for editing the video. And the streaming platform, we started with YouTube, and then we switched to Vimeo. And the first public performance happened, as you can see, at the beginning of the lockdown. So this was April of 2020, and this is what we looked like performing that particular session. So we started doing this regular concerts, 1 hour long duration. The core group of 6 performers that I mentioned before, many invited guests, either musicians or visual artists that would do, for example, painting in real time, inspired by the noises we were making, and this was all being transmitted through video as well. And we have been doing this for the duration of the pandemic and beyond. So the last concert was at the end of October, and it was number 105. So somewhere we have stored 105 hours of music that you can access. This is all archived in Vimeo. And 1 record release, which was organized by Chris Chafe and embodies one of the sessions. I believe it's session number 87 that he liked, and it has been released, and you have the link there. Not in this talk is Konstantin Basica's amazing video work in streaming the visual part of the quarantine sessions, as they came to be known. And he's using a mixture of Chromium plus a plugin that's called Pop-Up Jitsi, which enables to select individual feeds from the performers coming from Jitsi, this meeting server, and stream them and mix them in OBS, which is an open source, again, video mixer. And it goes from crazy things like this. So this is, you might be able to piece the performers in between this highly processed video stream, and we're all there, to something a little more subdued. So this is number 48, to something really aesthetic like this, which is number 105, where we're, in this case with 3 guests performing with us. So problems. As soon as we what do you need?
The presentation, the video.
Oh,
is it connected? Yes.
I'm connected. Yeah. Maybe not the right one. Oh, okay. So the problems. Right away, we said mono is not enough to properly present 6 or 10, up to 10 performers over a connection. Home internet was instantly a problem, so we were all in our places, and some of us were fine. Some of us had insane problems. I was one of them. I couldn't almost not perform at the beginning, and I could speak for an hour about just that. Hard audio clipping, so maintaining a mix where that can't happen. That was a problem right away. How to keep a dynamic range that is reasonable in the final mix. And finally, trying to create a sonic shared space where all the performers are kind of virtually located, so that they're glued together, in terms of the audio scene that's been broadcast. The software evolution, I'm going to just outline it very briefly. We started using Jacktrip in hub mode, just Jacktrip itself. Then we added some Super Collider software that was being written by Henrik von Koller. I added more code to that. And eventually, I moved to some software I had been using right before the pandemic to do performances, which was called Super Loopy, which was a multiple asynchronous looper that had some processing happening inside of them. And I transformed that to also be a mixer for the performance. And many changes over time, and it's currently being controlled through one of these fader boxes, the Behringer X-Touch, the simplest one. So this is where things are happening. So the 3 green squares are at Karma, at the Center for Computer Research in Music and Acoustics, Computer Music, at Stanford. And there's 3 computers involved. One of them, the one that says Computer at Karma, is a big Linux workstation that's acting as the audio processing workstation for the whole performance. The one below, the one that says Mac at Karma, is the one that's taking care of the video processing, and Konstantin is working with that. And I set up our own instance of Jitsi in one of our servers, so we could have complete control of it and modify it, configure it so it uses the best possible video bandwidth and all that. So you can see also the different performers are running Jacktrip in their home setup. They're also connected with some camera to Jitsi, but they're all going into this audio processing computer. One special case is Konstantin, which is also connecting to the video processing computer so that he's managing that. And another special case is my computer, which is also connected to the main audio processing computer. I'm using Super Collider, and if you know about Super Collider, the language itself runs separate from the audio engine. So the language and all the GUI and interface is running in my home computer, but the audio processing is running in the remote computer at Karma, and there's a TCP link with OSC messages that links both, and it works out. And then that computer is also connecting to this jack trip here. The audio stream which I'm sending is mixed and delayed in OBS, and that's what's being sent to the streamings where there can be a live audience listening to the concert with a few seconds delay, of course. So the software that I'm running, which is what I'm going to be briefly talking about, has kind of this block diagram. Almost all of it is running inside Super Collider with this program that I'm still developing. It has 16 possible input channels, so we could potentially have up to 16 performers running at the same time. I think the max we did was 12 at some point. It has the loopers, which are kind of optional, but I have been using them in performance. And then it has, the whole thing is mixed in ambisonics, in fourth order ambisonics. If you know about it, it's a format that enables you to describe a sound field. Everything, the spatialization of the sound is done in ambisonics, and then it's decoded to binaural, and then it's mastered in real time, and that's the stream that goes out. So a stream that goes out is 2 channels which are mastered and represent the full sound field in binaural format. I'm also capturing the full ambisonics mix in an external recorder, and this is what I look at when a session is happening. So inputs, loopers, global and individual controls, metering. You can see here these little arrows are pointing to where the stereo sources are coming from, and they can do, and we'll see they do dynamic panning also of the performance, so that the mix is not a static, but it changes over time. So if we zoom into the hub server, we're using a patched version of Jack Trip that automatically connects the performers to the proper inputs and outputs of Super Collider, right? So nothing happens inside Jack Trip except transporting samples to and from the performers. The mixing of the final mix happens in Super Collider. So Jack Trip uses Jack, which is a sound server, to do connections, and Super Collider also uses Jack to do its own connections. And what has to happen is when a new performer connects, there's going to be ports that appear in Jack that need to be connected automatically, and that's happening inside Jack Trip with this patch that I wrote, which is pretty simple. Another highlight I wanted to make is for the binaural decoder, which is also running inside Super Collider. I used code based on SCHOA, which is a quark written by Florian Grand, based on work by Pierre Lecomte and others. And after a lot of experimentation, and again, this could be a long talk if I talked about all the details, I found that this particular set of HRTFs for binaural listening were pretty good. They gave a very wide image of what's happening, and it's using the old SETI database subject number 2, which is a Newman virtual, head. And of course, the experience will be different for different listeners, because it depends on the shape of your, little chunk of meat here, that if you look around, you'll see everyone is different. So this one works very well for me, and the other core performers were also happy, so that's good. Another very important part is this little chunk here that says Master Me. And that's Klaus Schermann, which is one of the 6 core members of our performance group. At the very beginning said, oh, well, I could write something to do, real-time mastering, because he has been a mastering engineer for a long time. And he did write something called Master Me, which is written in Faust, and it's available in GitHub, and it has been an amazing resource because it maintains a proper LUFS, loudness unit relative to full scale, for the whole performance that is stable. It preserves dynamic range, it avoids clipping. It looks like this. The latest version, if you run it standalone, has a GUI. It looks like this in simple mode. You just set your target LUFS and off you go. Or you can go into expert mode and tweak everything. And it's a very, very good mastering system that works in real time, doesn't add latency, and it keeps, it solves one of these problems that we had, which is both dynamic range and clipping at the mix stage, maintaining that under control. So it can be compiled to pretty much everything, and I'm using it compiled as SuperCollider EUGen, which I incorporate inside the program that I'm running. So the solutions that happened during the course of this past 2.5 years is, for mono is not enough. We now can send, each performance can send a stereo feed. Each feed is mixed actually into a audio scene using 3D full surround ambisonics. The feeds can be assigned initial directions and stereo width. And the SuperCollider program also has some mostly level triggered automatic panning functions where the sources change position in interesting ways, I hope, when there's new onsets, for example, or when there's a silence. And that's part of the instruments that I have been developing that is inside the SuperCollider program. For the problem of hard limiting and clipping, at the source, meaning each client, Julius Smith at Karma wrote a set of Faust jacktrip plugins that includes a limiter. So the performers can activate that so that there's no clipping on their end, right? And that has been very useful. All those samples are going to be transferred to the main jacktrip mixing hub, and eventually they make it out to this mastering station where you have a reasonable level, maintain dynamic range, and avoid any sort of clipping. And of course, Klaus wrote Master Me, that's the important part. As to the question of shared space, I added ambisonics reverberators, and that helps a lot in gluing all the performers together, right? And furthermore, I have used sometimes reverb as a creative tool during the performance because I can change the virtual space in which the mix is happening in real time. As for the latency problem, well, there's latency due to geographical locations, and that's unavoidable. But a lot of optimization has happened inside jacktrip itself during the past 2.5 years, and that would be another talk, to have, because a lot has happened, and for the better, and it's a great tool. At the beginning of our sessions, we had to run with 1,000 sample buffers. Right now, the main server is running on 128, so that gives you an idea of progress that has happened. And the bonus has been also the incorporation of this Super Loopy program that I was developing before, where we get asynchronous loopers that I can use during the performance to capture some of the performance and then present these materials again later during the performance. So sometimes I use it a lot, sometimes none at all. It depends on what's happening in that particular session. Still to be solved, internet home connections are much better than before, but there's still instances of drop packets causing glitches, and Chris Chase is actually doing work in concealing those things. So instead of repeating something, or instead of getting a little bit of silence and a glitch, he's merging in surrounding samples, trying to hide it, and it's becoming very, very effective. Still to be solved. Well, this is a difficult problem. How to keep a wide dynamic range in the final stream. Some performers, especially guests, tend to send already compressed streams, and that's a problem. You get into a loudness war, and it doesn't work. The solutions, I don't know. I mean, this one I like better. Educate performers. Tell them no, don't do that. But sometimes we do a sound check at the beginning. What's the loudest you're sending? And you get something. And then during the performance, you get a lot more, and it's like flat. So it is a problem. And still to do, the fact that we're using a patch jack trip can be solved. I did some tests. You can do that from inside Super Collider and Supernova, so that you could run with a jack trip that's stock, plus the Super Collider program. But there's problems also. So if Constantin is not available, where's the video coming from? Because he does the magic for that. Or if I'm not available, where does the audio processing come from? And we have found solutions for that. Not optimal, but that's it. And we have been working for this 2.5 years, and it has helped keep us sane during the pandemic. And I will very much regret when we stop doing it. It's not as often now as it was before, because people start having so-called lives, and they're busy, but we'll try to keep it going for as long as we can. And all of this is archived in Vimeo. If you go to our website and look for past performances, there should be links to the video and audio. And that's it. Any questions? Or any answers, that'd be even better.
Yeah, thank you for the talk. It's very interesting. I'm really interested in this area. I've been following it for a long time. Kind of the prospect of online collaboration for musical performances. And it seemed during the pandemic there was a number of different attempts to do it. In your instance, are people playing acoustic instruments simultaneously? Yeah,
what is being played, it depends on the mix of performers at the moment. So the 6 members of the core group, I do electronics mostly, and some stage piano. Chris Chafe plays his celletto, which is a cello which is hollow and electronic, and sends the individual strings, all the 4 strings, or a Dilruba or other instruments he has. Klaus is electronics. Juan Parra is electric guitar and processing and modular. Henrik von Koller is doing a bunch of things. He has some very old oscillators. He has some objects and contact mics that he manipulates, and he has a special controller. Guests have played everything. So acoustic instruments, trumpets, guitars, and they all interact at the same time, and we play music that can be played with the latency we have.
I understand. Yeah, that was kind of my next question. So I presume it's kind of an improvisational jazz kind of thing where you're not all trying to land on a chorus or on a beat.
Sometimes it happens that we have a pulse going and we are able to sing. Sometimes not. It's free. Sometimes before the session we say, well, what shall we do? Especially if we have guests, and we say, okay, we start and then we shut up after 2 minutes, and you, the guests, will have a solo for 5 minutes, and then we start coming in at different times. Sometimes we don't say anything and we just go for it. We have, after 100 performances, we have some sort of understanding, and we react, and we're all of us were listening to what's happening and reacting in real time. But of
Okay.
course, it's not pulse-based music. It's whatever can be played, and it depends on what the performer is. Especially the guys in Europe, have a hard time because our server is in the United States. But like, pipe organ players, you can get used to playing things with some lag. It's not ideal, but I mean, unless one of you guys have a solution for the speed of light problem.
Okay, great. Just if you don't mind as well, I'd be interested to hear your thoughts on why, let's say, the music collaboration on the internet like that hasn't taken off really in the broader sense. What do you think are the main obstacles?
Well, in a sense, it has taken off compared to before the pandemic. So a lot of groups are collaborating over the internet where this was not happening before. There's a human aspect of being in the same room and performing with other musicians that is diluted a little bit when you do a remote performance. There's also still a technological barrier, a price of entry into the club, because you have to master a few things which are not very difficult, but there's so many things that can fail or not be optimal. You have to have everything, and sometimes it's something as silly as suddenly we can't figure out how to turn off local feedback in the computer that the guest is using. Or sound doesn't come out, and it's because there's some routing in the local chain in the home of the performer. Something is not routed correctly, and sometimes it's difficult to figure things out because of the many types of systems and software that people use.
Okay, thank you.
I think it was first.
You spoke about how you send audio to the server on the streaming service, but I know that on stage musicians like to and need to have feedback of other musicians. So how you working with this?
The audio that is sent to the audience through streaming is exactly the same audio that is being sent to all the performers. So the performers don't, some other software has the ability to do a local mix, for example, that's different from the one that's been broadcast. In our case, we are listening to the final output. So everyone knows what his or her contribution to the mix is at a given time. So I guess that's the glue that gets everyone together. That can be a problem sometimes. If we get guests that are not used to performing with any latency at all. And we don't currently have, I was working on a solution to try to change that so that selected performers would not receive themselves mixed in the final mix, right? So that they can have their local monitoring to hear themselves without latency. But it defeats the purpose in a way. Because the purpose is that you listen to the final mix, you are in the same room, basically. I don't know if that answers the...
So just while we take the next question, Nando, can you unplug your computer so that Maxime can,
of course,
can connect? And,
Go ahead.
Yeah, well, my question was kind of related to the previous one on local monitoring, because it's something that I've seen that, yeah, you are using binaural decoders, because I guess you are, they are all with headphones, right?
Most of us use headphones.
Yeah. Is there any, when you play, for example, electronics, and then you have local monitoring with the speakers, how have you dealt with the issue of having feedback or, delayed version?
Yeah, I don't use speakers. I always perform with headphones. I think Chris Chafe uses speakers, and he's fine. I'm not sure. Okay, Henrik and Klaus. I think they're all the guys in Europe use headphones, so they don't have that kind of problem.
Right. And just 1 second, have you thought of implementing, for example, impulse-response convolutions for adding, instead of reverb, a real feeling of a room?
No, that's part of what we do. So I have an impulse response real-time convolver, partition convolver, that is ambisonics. So it's proper reverb that's being mixed into this, and there's 2 reverb units, one which is a feedback delay network reverb, artificial, and the other one is convolution. And I've been using a modified version of an impulse response of the York Minster in England that's published, that's first order ambisonics, and that works very well. I like it. And sometimes I crank it up, and suddenly we're in this huge space.
Thank you.
And that really helps to put everyone in one place, which is one of the problems with this. And I think we should move on to... You can ask any more questions later. Yes. You need this.
Thank you. J'essaie de débrancher.
Yeah, for those of you who are watching us remotely, there's a problem with the screen copy, and it's pretty common with video streaming. So we're really sorry about this. So for now, you're going to have to just deal with the camera. During the break, we're going to try to fix this, but for now, we just need to keep going. So sorry about this. Anyway, so now we have Maxime Popov, and Maxime is going to talk about high-level programming of FPGAs with Faust for real-time audio signal processing applications. And thank you, Nando, for your presentation.
Yeah, thank you very much. So, hi everyone. My name is Maxime Popov. I'm a PhD student inside the MWOT team, and today I will talk about high-level programming FPGA with Faust. So the MWOT team is a team inside the City Lab, which is in this building. It's a collaboration between INRIA, INSA Lyon, and GRAME CNCM. It is the Stifala project, basically, that Loic told you earlier. So what is the Cifala project? Well, the idea is to make sound on FPGAs. So an FPGA is a very powerful embedded platform. So I will explain later what it is exactly, but just admit for now that is a very high performances platform that you can program. So we want to use those platforms, but we want to make their use easy and easy for the audio community. So we want to use a high-level programming language, like FOSS, for example, which is very used in the audio community, to make the programming of audio DSP on FPGA easy. So this is the idea behind Cifala. Cifala is it takes the shape of a command line in Linux. It's a compiler. And so, yeah, here it is. So what is an FPGA exactly? So it stands for Field Programmable Gate Array. So the field programmable is because basically it's reprogrammable. It can be obvious, but it's not because it's hardware. So it's the only way to reprogram hardware is to use an FPGA. It contains a lot of little logical block, very simple function that you're going to use to program them. So you have a lot of them, you wire them in the right way, and you can do your function, right? And so, yeah, array because there is a billion of them on one FPGA. So, yeah, an FPGA is really a little chip. It's like 1 centimeter per 1 centimeter of silicon, and you have everything you need on it. So, what exactly are these logic gate and this little block? Well, it's some small logic block that you have. I'm going to explain later what's inside it. So, you have to compose with them to do the function that you want to do, right? So you have a lot of them, you choose them and you configure them the way you want, for example those one, and you will connect them the way you want. And then you have your function, your hardware function. Those little blocks, it's called configurable logic block, CLB. So it's made of one lookup table and one register. So it's allow you to do any logical function n-to-1. If you want to do a logical gate or a NOT gate or OR gate, you can do it. You can do a multiplexer, you can do a custom state machine. Every logical block can do that, and you have billion of them. So if you connect them the right way, you can do any logical function that you want. So the idea is that there is a register. So you have the idea of clocking thing. This is not just you put something in the input and you have output. You can really process serial data, you can process parallel data, you can do a lot of things with them. So yeah, you can really do any hardware function that you want. You have other blocks inside the chip, so you have memory blocks, it's called BRAM. It's a very fast memory, but there are few of them. You have some DSP blocks, it's specialized block for mathematical function. And you have some clocking blocks, so you can do some PLL and something like that. So this is the idea behind the FPGA. You have your logical little block. You wire them the right way, you configure them the right way, and you can do any function that you want. Here you have, for example, two different functions. They are very simple on this one. So it's configurable hardware. All right. You don't by hand wire every logical gate. It will be a very long process. So you can program them using a language. It's called a hardware description language. It's a special programmation language that we will see later. But yeah, you can program them using a language. You don't really program them because there is no software. So we talk about configuration. You configure them, you don't program them, but it's kind of the same. So yeah, what's the difference with a CPU? Because you probably know how a CPU works. So on a CPU, if you want to do any instruction, let's say you want to do an addition, the CPU will fetch the instruction, decode it, take the arithmetic and logical unit to make the computation, store the instruction. On an FPGA, you really have the hardware function that is code, right? So it's very fast. You put some input, you have the output. It's physically here. So here, for example, with an addition, you take one logic block, you do a XOR gate with it. You take another logic block, you do an AND gate with it. You connect them the right way, and you have your adder. Okay. So The only thing that limits the thing you can do on an FPGA is the number of logic blocks, basically. If you, as long as your function can fit in the number of logic blocks that you have, you can do any function. On a CPU, you will be limited by the frequency of your CPU and by the number of core. So this is really not the same needs. So what can we do with an FPGA? Well, basically, you can easily parallelize things. If you have your function, you can just duplicate it, and as long as you have enough resources, again, you can duplicate it how many times you want. So this is pretty nice for parallel data processing. You also have lots of input and outputs on an FPGA, like 100 of the one I work with. So you can do a lot of parallel data processing. So for audio, for example, you can imagine multi-channel that can be handled easily. On a CPU, if you want to really do some function exactly parallelize them, you have to do one function per core, so you will be limited to 4 or 8 maybe. So you cannot do that really. On FPGA, you can really parallelize 100 functions if you want. You have another thing, pretty nice. You can pipeline things. Okay, so if you want to process, let's say, some serial data, for example, some sample of audio, with for 3 functions. So you can imagine that every function is a block, a physical electrical circuit in one block. On a CPU, everything going to be sequentialized. So you do every function, you have your data 1 goes out, the next data goes in, 3 function, data goes out. And you can pipeline things on a FPGA. So you put the first data on the first function, and when the first function is done, you can instantly put the second data. You don't have to wait for the first data to be fully processed. You can just put the second one as long as the first block is available. Okay, so you can pipeline things, and it's really increase the throughput. As you can see on the first example, it takes like 9 time slots to process 3 data, where it takes only 5 when you pipeline. So it does not reduce the latency. In both cases, one data takes 3 time slots to be processed, but it increases the throughput. Okay, so this is an FPGA basically. This is why they are pretty interesting for real-time audio processing. You can have high throughput, very low latency. I will talk about that later. You can have a high sampling rate, like more than 20 megahertz, for example. You can have a very high number of input and outputs, and you can do some parallel data processing easily. So they are already used for audio processing, not a lot, but they are already used. You have some example here. So, for example, for the Innovation Summit keyboard, they are used for very specific function. So it's only for a very high audio sampling digital oscillator here. But they're already used. They're already interesting, but not a lot. Why? Because they are very, very difficult to program and to use. So I have a little example here. It's a little bit biased. I'm going to explain. If you want to do an edition on C, you will just have this line. On an FPGA, it's a little bit more complicated. First, you have to declare everything, every interface. Here, if I have 2 signal input, 2 signal output, I have to declare everything. And you have to do your computation. So here, it was just to show you that you can basically say that you want an XOR gate and an AND gate, and you do your electrical circuit. I could have used a plus, so you can just use the addition here, but still you have to do all the interface around it. And this is not the only problem, because you have a lot of engineering questions to answer when you program FPGA. Do you respect the timing? Do you respect the latching of your input signal? Because you have your input, you have to catch it at the right moment. You have to do a test bench. So basically a test bench, you have to simulate every input signal, and you will just see the output that it gives you. And you have to check if the output is the right thing that you want. So at the voltage level, I mean, it's a pretty long process. Do you have enough resources? Again, on the CPU, if you ask for a long algorithm, it's just going to take a long time to execute. Here, if you don't have enough resources, it won't fit. So a lot of questions that aren't simple to answer, and this is basically why we don't use it more, especially in audio community, because it's very specialized and not everyone has those requirements to answer those questions. So this is what is an FPGA basically. So you have one part of the project, and so the other part is how we make it easy for audio community to program. So using FOST. I suppose a lot of you know what FOST is. So it's a programming language. So it's it's a functional programming language, and it's made for sound synthesis and audio processing. Okay, so it's developed by the GRAME CNCM, and it's very accessible and very used in the audio community. So that's a good start, because we want to make FPGA used by the audio community, so we use a language that is used in the audio community to program them. And something pretty interesting is that it can be translated into a lot of language, and especially for our case, in C and C++. We'll see that later. So now you should be able to understand this slide. So this is the idea behind Cifala. You use FPGA with high-level programming. So there is another problem, more than just the programming of them. I'm going to show you this example. This is some FOST code. You don't need to understand it if you don't know how FOST works. But the idea is that we want to do, we want to implement sine oscillation and put it inside an echo on this example. So the way that the sine is made, it's use a resonant filter. So we just need to compute the cosine value and the sine value of the frequency we want, and the filter will generate every sample of the sine. Okay, and we put it on an echo. So if you just put that entirely on an FPGA, maybe it will fit because it's a very simple function, but it will use a lot of resources. Why? First, because the echo, so an echo, if you do a 1 second echo at 48 kilohertz, you will need 48,000 samples of 24 bits. It's a lot. It won't fit on the block RAM that you have. You don't have enough memories. And the cosine and the sine function are very, very costly in FPGA resources. So how can we resolve that? Well, we don't use an FPGA in standalone. We use a CPU with the FPGA, so an ARM in this case. And the idea is that you can put every computation at the sample rate on the FPGA, and every computation which is at the control rate, you put them on the CPU. So you keep the fast computation of the FPGA, but you can dispatch some computation on the CPU. So for example, if I take the example just before, the cosine and the sine function, they need to be computed just one time. So we can do them on the CPU. And if we change the frequency, they need to be recomputed one time, but it doesn't matter if you don't do it at the next sample. You can wait 2 or 3 milliseconds. So you can do them on the CPU gives the value on the FPGA, and the FPGA do the sampling rate computation. And same thing for the memory, so we can use an external DDR, which is pretty slow, but it's very big, so you can store a lot of sample on it. And if you just need to access some sample per sample, it will be okay, because you have like a 30 access that you can do between 2 samples. So that's not a lot, but for an echo, I mean, it means that you can implement 30 echoes, so it's pretty nice. So yeah, this is the idea behind the balancing of computation. So this is what the Cifala toolchain will do for you. It's not only a FOST to VHDL compiler. It's also, it do all the balancing. It interfaces the CPU with the FPGA, with the DDR also. It does the design choices for you. We can do that because audio program tend to have the same problematic. So you will mostly have the same amount of memory needs, of the same memory dispatching, the same resources dispatching. So you can determine what an audio program is, and you can do the rule inside the compiler. And yeah, it's also dealing with a clocking issue, for example, which is a pretty big issue that we have. And yeah, so how can we do that? thanks to Force, so I will explain that in a better way this afternoon at the workshop, but Force can generate two different files, and because we modified the Force backend. So you can have one file with all the sampling rate computation and one file with all the control rate computation. And so from that, you can execute the control rate on the ARM and the sampling rate on the FPGA. So for the ARM, it's pretty easy. It's just a C++ file. So you just have to compile it with GCC, for example, and you can execute it. For the FPGA, it's a little bit more tricky. We use the high-level synthesis tools. Those are a software that is provided by the manufacturer of the FPGA, and it allows you to take C++ files and transform them to what we call an IP, an intellectual property, which is a hardware block that you can directly implement on the FPGA. So you have to tune the tools a lot, but we already do that for you, so you don't have to. And you can directly have your physical function from the Force program and from the CPP file, C++ file. So this is CFALA, basically. You write something in Force, maybe a physical model of a MooBox. You just have the command line CFALA. You have a lot of options that I will explain this afternoon during the workshop. You wait 15 to 30 minutes. It's long, but it's not very long for an FPGA. It takes a lot of time to do the synthesis and the implementation on an FPGA. Most of the time we talk about hours, maybe it's day. So here, 30 minutes, it's pretty nice, but you have to wait anyway. And you have it. You can directly flash your FPGA, and you can have the first MooBox in the world with an FPGA inside. I don't know why, but you probably want that. So yeah, this is just that. We tune everything for you. So let's say you want something maybe more interesting for music. You can control the FPGA using two solutions. You either have the GUI, which is automatically generated based on the Force that you write. So it's on your computer, right? And you can control the FPGA through the USB cable. You can use a MIDI controller to control this interface. So you can control your FPGA with a MIDI controller. Or you can use those open hardware board that I make. It's just 8 slots, and you can choose between a slider and a knob or anything. And you plug it directly inside the FPGA, and so you can have a physical hardware to tune your DSP. So we did a lot of work for ultra low latency. The thing that I didn't speak about for now is that you have to have this little interface between the audio analog signal and the digital signal that you just compute. So these are called codec, audio codec. It's just an ADC and a DAC, but with a lot of filter for audio signal. And you have to use them. You cannot put some analog signal into your FPGA. The thing is, when you want low latency, this board is pretty slow. For example, our computation on the FPGA, we guarantee you that it will take only 2 samples to do any computation that you want to do, as long as it's fit on the FPGA. So we have 2 sample latency. So at 48 kilohertz, it's 40 microseconds. But the audio codec will add a lot of samples. For example, the first one we used, it was, I think, 50 samples of latency. So we try some very low latency audio codec. The lowest latency that we can find was the ADAU 1787. And thanks to that, we were able to reach the latency, the round-trip latency, so analog in to analog out, of 11 microseconds. So it is at 768 kilohertz. So it's allow you to do very, very low latency system. And because those codecs can be parallelized, you can have a 32 in, 32 out system at 11 microsecond latency. So it's very promising for active acoustic control, for example. So to do that, I designed this pretty big board. So it embeds a lot of audio codec, ADAU 1787. So I designed this board. You have the little chip here, which is the audio codec. you just plug 16 of them, and you have your 32 in, 32 out board, which is directly connectable on an FPGA. And you could theoretically, I didn't try for now, stack 16 of them. You have enough resources for that, and so you could probably have 512 in, 512 out system with 11 microsecond latency. So yeah, Cifala is already used in some other university. You have some example here. So it's used in Menus in Ireland, in Yale in Singapore. So it's used by the École Centrale de Lyon. You just saw the presentation this morning. And we have a collaboration with the Karma at Stanford University. We work on WFS with them, so wavefield synthesis. And especially thanks to this future board of 32 in, 32 out, low latency audio interface. So what's next? We have some work to do. We try to embed a Linux right now. So on the CPU, you will have a small Linux that run. So you can add the Ethernet connection, for example, or a lot of interface. We try to use a force to VHDL backend, which will eventually allow us to get rid of the HLS high-level synthesis tools in the future. We have some memory accesses improvement to do. There is Florent de Dinchin, which is a pretty good researcher on the mathematics that will work on the fixed point, because right now everything is in floating point. So we want to implement a fixed point version. And for now, we don't pipeline anything. We can do that. We want to work on that in the future. Yeah, thank you. So this is the QR code of the GitHub, but you have the address just here. And yeah, I have a workshop this afternoon when I will explain more technical detail about the compiler. Thank you. Question? Yeah.
So you mentioned the ARM and the Xilinx chip. So you're using, is this only working on those specific Xilinx chips that have the ARM?
Yeah, so yeah, I didn't mention that. So yeah, basically you have two big manufacturers of FPGA. You have Xilinx and Altera. For now, everything works with Xilinx. So we made it work with some Zibo boards which embed Z7, Zinc 7, and with a Genesis board that embed UltraScale Plus FPGA. So for now, we are sure that it works with that. It should be easy to make it work with other Xilinx board, but for now, it don't work with Altera product, for example. First, because we have to change every script, and also because the high-level synthesis tools are provided by Xilinx. So Altera provide the equivalent, I think, but we didn't try for now, so yeah.
What about the open source toolchain in RISC-V CPUs?
Yeah, well, we didn't try yet, but I don't think there is a high-level synthesis tool equivalent, so...
There is.
There is? Okay, so we didn't try. But yeah, we have to start with. It's already a lot of work to understand how the tools work, even with something like Xilinx, who provides a lot of documentation. So yeah, we start with those one, and we'll see after for the other one.
More questions? Yeah.
Hi, I'm just wondering on the CPU. So you have the CPU and the FPGA.
Yeah.
On the CPU, is that running bare metal, or do you have any kind of a free an RTOS or?
Sorry.
Is it running bare metal, or is there an RTOS on the CPU?
Right now it's running bare metal.
Okay.
But yeah, we try to put a Linux on it. But right now it's bare metal. So the CPU don't do a lot of things. It just check the input, so the ADC with the potentiometer and things like that, and it just send the value of the computation to the FPGA. So right now it's just bare metal, but we could add a lot of things on it. The thing is, we use a system on chip, so it's on the same silicon chip. You have the FPGA and you have the CPU. So it's not a CPU implemented with the resources of the FPGA. It's really you have the architecture of the CPU, so you can put a lot of things on it. It won't take the resources of the FPGA. So yeah, for now it's bare metal.
Okay.
Just to precise something, we divide the control code and the DSP sample level code, and on the CPU we can do a part of the initialization code is done on the CPU, and then we can share like tables for sinus kind of compilation or this kind of thing. And when we are doing a sample level thing, everything coming from the control, there is a bit of processing done on the control, like doing some computation which depends on the controller, and then we send updated values to the FPGA using the DDR transmission between the two sides, basically.
Thank you for the speech. Just you have shown a picture of your you made a board containing the analog inputs and the audio codec chips.
Yeah.
And then that board is then connected to the system on chip.
Yeah, through the FPGA, yeah, through a FMC connector, yeah.
And so you made a custom board for.
Yeah, so this one is just 3D render for now because
okay.
I just received this one yesterday, so I have to test. This is the little chip that you want, you see on it. Yeah, because I want something modular if I want to add or
very good.
Codec, and because the codec are the expensive part, so I don't want to solder everything on the board. So right now I just have the little board. That's that should work in the next days, I hope. And so after that, this is basically just connection. It's just you have from this little board you already have your input and output, audio input, audio output, and the digital signal. The codec handle everything, so you don't have anything to do. So you just have to connect 32 audio jack to that. This is what this big board do, but it's just wiring. It's just to avoid me to do 32 soldering on each jack.
Yeah. And then the FPGA is on a separate board or underneath.
So
or
this is this board is like 20 centimeter per 20 centimeter, and we have evaluation board of an FPGA. We do the same size, so you just stack on it, and there is a connector. There is not a lot of GPIO needs for that. It's like 20 GPIO for all the board, because every audio codec takes only 2 signals, data in, data out, and you have the 3 clocking signals that are generic for every codec. So you have 2 times 16 plus 3 GPIO, and you can time multiplex. So you can even on the same number of GPIO, you can do that 16 times. Yeah.
Yeah,
so
I think it's really cool.
Yeah, I hope it will work. For now, still in progress, but.
Are there any questions online or no? Okay, cool. So I think, well, thank you, Maxime.
Thank you.
We're going to take a 30 minutes break. So we will resume at 11:30 sharp. We're going to try to fix the screen issue for those of you who are watching us remotely. There is fresh coffee in the lobby and cakes and stuff like this. So yeah, feel free to grab them. And so we'll be back at 11:30. Thank you. Okay, welcome back. So we now have Chris Kiefer, who's visiting us from the UK, and he's going to talk about signal processing with machine learning on FPGAs.
Thanks, Roman. Hi, I'm Chris. I'm from the University of Sussex in the UK, the Experimental Music Technologies Lab. And what I'm going to talk about today is some research, well, leading into some research that I've been doing about using machine learning on FPGAs for musical creative practice, really, and why you might want to do that and how it's useful for us as musicians. So I think the kind of main point I'm going to try and make is that FPGAs offer us something kind of new ways that we can use machine learning that are quite suited to music and musical instrument design. But also, we've got a lot of challenges in getting there. There's not a whole lot of research going on in this area at the moment. FPA is quite challenging to use, as Maxime has already pointed out this morning. So I'm going to kind of lead into that, think about machine learning in general, and kind of zoom into why we might want to do it with the FPGAs. So I didn't know how much people do machine learning in the room or who are listening online, so I'm going to make a really probably grotesque approximation of what machine learning is in 2 slides. So here goes. Well, normally when we're configuring machines, those machines are usually computers of some sort. We use code, we hand code it, and that gets us so far. But if we want to do something a bit more complicated, we can, if we want to try and get machines to do more complex tasks that we can't achieve using code, we can take a different approach, which is configuring machines with data. So instead of directly programming them, we have some process that we have some data, and we get the machine to behave according to how that data is. So that's my really kind of rough idea of where we're going with machine learning today. And in music, we probably already know a lot about this in this room. We can do a whole lot of interesting stuff with machine learning in music. We can use it to generate audio, we can use it to generate notes, we can do things like text to audio, which is quite exciting at the moment. There's a whole lot we can do with configuring machines to do machine listening. We can make signal processors, we can do some very exciting stuff with recognizing and mapping gestures. So all in creative work, machine learning gives us some real opportunities to do interesting stuff. It's really worth thinking about how machine learning fits into the creative process before we start thinking about how FPGAs fit into this and why they might be useful. So quite often this is the sort of situation we're in when we're trying to use machine learning in a musical task. We've got some kind of, this is very, very high level, we've got some kind of tunable model which we configure by training it, some sort of optimization process. This model is situated within an environment, so that way it might be a musical instrument, it might be something online, it might be in a performance environment, and the creative part is trying to get this model to do what we want musically, and so we optimize it in various ways, and we change how this model is communicating with the environment around it. And when we're doing this, there's various different tasks that we might think about following. So, and these are all usually creative in some way. So we have might be doing data curation, so that would be collecting data which we configure our machine with. We might be doing model curation, which is trying out different models that we're optimizing. We'll be training these models and doing some sort of evaluation. So that might mean improvising, making music with these models. So that's the kind of world we're in with machine learning, with music and creative work. So I'm going to kind of start thinking about contemporary machine learning, which tends to use some kind of different hardware from FPGAs, and kind of zoom in into thinking about how FPGAs might be useful. So many people probably know quite a lot about this thing called deep learning, which has had a lot of success at the moment. We hear a lot about machine learning and AI and the different things it can do. There's a lot of very interesting stuff going on with large language models, for example, being able to generate text, text to image, stable diffusion, so being able to generate images and videos from text. And there's a kind of lot of very interesting work happening at the moment. And a lot of these approaches follow something called deep learning, and I'll talk about how that relates to music in a second. But as this is really about hardware, let's think about how we run these deep learning models. So when we're doing deep learning, we tend to be using lots of hardware. So some of these large language models which have been happening recently have used kind of hundreds of GPUs to train. I think Stable Diffusion took quite a huge amount of effort to train that model. And so there's a lot of energy and a lot of expense and a lot of hardware that happens in deep learning. We tend to need GPUs because we're doing a lot of matrix multiplications in parallel. And so these models are quite demanding resource-wise, which is great, that's fine, but how does that relate to when we want to use these things musically? So if we're going to use deep learning approaches, we need to think about things like having a lot of memory, having large amounts of parallel processing, probably needing lots of energy to train and to use the models, and actually physically the machines we need are quite big. And we can think about how that relates to music. So in music, there's a lot of exciting things going on in deep learning. So a couple of examples, maybe people have used rave models in the room. Rave models have come out of ERCAM recently, and they're a really nice way of doing training a model on unsupervised data. So showing this model lots of audio and then being able to generate stuff that sounds like that audio, or using it for timbre transfer, so playing an instrument into it and changing the sound of the instrument based on the data that you've shown this model. So that's a really successful thing at the moment. There's lots of things happening at the moment, so I'm just picking out a couple which to set the context. Also, Audio Gen, which just came out from Meta, which is a text-to-audio model, which is sort of exciting, the kind of audio equivalent of Stable Diffusion. So you can give it a text prompt and it'll try and invent that in audio for you. So they've got quite a fun web page you can go to which gives you an example of the prompts that have been kind of rendered as audio. And there's also lots of things going on in audio diffusion and state space models, so lots of and kind of long-term sequence prediction. So deep learning is really fantastic, but it also presents us with some real challenges with regards to creative work and how we approach it as musicians. And so models that rely a lot on GPUs are really challenging in terms of latency. And of course, as musicians, we want low latency. We don't want much of a gap between when we make an action in the world and when we actually hear the results of that action. And so, also in terms of training time, some models can take kind of a week or two to train, even though you can use them in real time. So I've been messing around with rave models at the moment, so it can take a day or a week to train a model to a high quality, even though you can use it in real time later. So in terms of creative process and how we engage with models, that kind of turnaround time can be a bit of an issue. Also in terms of heat and noise, maybe as in music, it would be nice to be able to use machine learning models embedded into musical instruments. But of course, if we've got if we need lots of GPU power, that's not really going to happen. It's going to be problematic. And even if we can use kind of small GPU boards, they can have fans, they can create a lot of heat, so it's not ideal to stick these things into a musical instrument. So this leads to some questions. So how can we take the kind of power of some of this deep learning stuff, but then think about how we can shrink it down and use it in a kind of smaller format, and maybe think about how this fits into creative workflows a bit better. So how do we kind of take stuff that runs on GPU farms and kind of get down to this smaller level, which I think FPGAs are a really useful thing for. So from deep learning, we've got this thing called TinyML. And TinyML is aimed at running machine learning models on smaller microcontroller platforms, basically. So the typical thing we're thinking about is things with small GPUs. They probably don't have extra resources like a GPU or a floating point unit. They've probably got very small memory, so think things like Arduino or Teensy, if you know those, so less than a meg, maybe much less. They could probably run on a battery, a 9-volt battery. There's probably only one CPU, so there's a lack of parallelism. But they're kind of probably very easily extendable, so you can kind of fit them in with sensors and hardware. So when a TinyML is approached where we take a trained model, so that might have been trained by something like deep learning, and we do some sort of process of reduction or approximation. Some people call this approximate computing. And we end up with an approximated version of this model, which we could call the tiny model, which is optimized to run on a small platform, something like an Arduino or a Teensy. So what can we do to do that? Well, we can do things like quantization. So conventional deep learning uses floating point or double matrix multiplications. So we can quantize them, we can approximate them by turning all the floating points into integers, which means we can run them on a smaller machine. We can do things like binarization, where we can threshold all the numbers and turn them into ones or zeros. We can simplify some of the functions in these models. So instead of using maybe stuff that use expensive trigonometry functions, we can simplify them into kind of integer threshold functions. And we can prune models down to save memory. And also we can slow down the data rates. So maybe instead of using CD quality sounds, we think, well, maybe we don't need that. We can slow it down to 16 or 8 kilohertz and see if it still works okay. So these methods are all about taking something that's kind of trained using on a larger system and then chopping away at it and hoping it still works well at the other end. And there's plenty of examples of some success in doing this. So this is a paper from 2016 by Kumar et al., where they managed to get some machine learning models running in 2K of RAM on an Arduino fairly successfully. Though inference kind of took milliseconds, not microseconds or nanoseconds. But they managed that quite successfully. XNORNet is another example where this group took the transfer functions of neurons in a neural network and changed it so it's into binary logic functions. And so then, once they'd done that, it was much easier to run that on a small computer. And there's plenty of stuff happening at the moment. Edge Impulse is an example of a tool chain that people are using for TinyML, which takes models and reduces them down to these kind of smaller form factors. A nice example I thought was this little thing here, which someone had used Edge Impulse for, where it's a metal detector. It detects heavy metal music. So it's got a machine learning model. It does machine listening, and it runs, I think that's either an Arduino Nano or a Pi Pico or something. So something really, really small, but it's doing machine listening. And it seems like there's a lot of work in this area around sound classification for whatever reason, but maybe there's not so much about kind of sound production and creative work. So it's more kind of functional work about sound recognition. So what challenges have we got in TinyML? Well, these models can be quite difficult to run at higher frequencies, let's say kind of higher audio rates. It's quite challenging to model some of the more complex processes, so we can use this for quite simple models, and maybe that's why it's been used for kind of simple sound classification so far. And we've also got some latency challenges as well, so a lot of microcontrollers won't do kind of low latency work. So then we can move on to thinking about, well, the next kind of step along in hardware for microcontrollers is to think about how we can use FPGAs for machine learning and for music. So Maxime has talked about FPGA architecture a bit already before today, so I won't go into too much detail, but this is the chip I'm using at the moment. This is an open source chip. It's called the ICE40 from Lattice. It's reasonably cheap. I think these boards cost kind of 40 or 50 pounds. What it lets you do is really, really fast signal processing. It's low power, so it's designed to go in mobile devices. It runs on low voltage. And it has an open source toolchain, which is quite useful. This is a diagram of how these chips look. And so you've got a bunch of these configurable logic blocks, like Maxime was explaining earlier, and you can configure this FPGA to kind of perform certain functions. There's not much DSP. It doesn't have a floating point unit or something like that. So this is kind of fairly basic. And this is the heart of it. You've got these things called lookup tables, which you can configure to perform certain functions. So TinyML and FPGAs, well, we can follow the same process. We can do some kind of reduction approximation. So we can take a machine learning model and we can kind of chop away at it, binarize it, and turn it into something we can run on an FPGA board. So usually this works out kind of producing a model and some kind of supporting logic to go with it, maybe some kind of arithmetic routines. And there have been some interesting examples using logic nets and binary neural networks. These approaches have been quite successful, but they do need fairly large FPGAs. They produce quite large models, and they still need some, let's say, abstractions, so things like maybe floating or integer kind of arithmetic units and stuff like that. So we need some kind of memory management and stuff as well. Here's an example of someone putting WaveNet. You might know WaveNet. It was a kind of generative AI model onto an FPGA, and they're kind of showing that it's had much larger performance than was possible on using a GPU. This is my own research, so I've been looking into alternatives, ways other than TinyML of something called stochastic logic optimization. And the idea here is to run very lightweight machine learning models on open source FPGA boards with the aim of thinking about how you can embed this stuff in musical instruments. Say, I have an electronic cello. I'd quite like to be able to take machine learning models and put them inside that cello or inside Eurorack modules. And the concept behind these is based around an experiment that Chatterjee did in 2018, showing that you could take networks of LUTs and get them to learn functions. So you don't, maybe the kind of previous wisdom was that you needed the complexity of how neural networks work to get a model to learn. But actually you can just learn things using logic gates. You can learn using logic gates. So the idea behind Slow is that it just uses binary logic. It's a very minimalist approach. There's no counting. So unless you think about binary as counting, so there's no arithmetic logic, there's no floating point, it's just raw logic gates. And you build feed-forward networks of these logic gates, and it optimizes them to perform certain functions. So the results so far in this, well, it's been shown that this system improves on Chatterjee's memorization, initial experiments, and improves on a genetic algorithm doing the same thing and a beat prediction task. And I've also been using these for sound synthesis, waveform generation, in conjunction with random Boolean networks, and something called PDM, pulse density modulation, which is a way of thinking about signals in binary instead of using continuous numbers. And I'll talk about that in the workshop a bit more this afternoon. So basically, you can this is a kind of reservoir computing approach where you take a dynamical system called a random Boolean network, which is made out of logic gates, and you feed signals into that, and you observe it with another network of logic gates, and you can kind of create feedback systems which will produce waveforms. So this is fairly early work still. As I said, there's not much work going on in this area, thinking about sound synthesis, machine learning on FPGAs. So to summarize, there's lots of challenges happening in this area at the moment, thinking about how we engage with machine learning using this sort of hardware. So it's quite difficult to actually kind of embed this straight in an instrument at the moment, which is really where I'm aiming for, because we still need to use another computer to train the models that we put on the FPGAs. There's not many FPGAs that will do self-reconfiguration, which means they can kind of they can change their own logic gates. So it's actually difficult to train networks in place on the FPGA, that a lot of them don't have much memory to help with that, so you can't kind of get a lot of data on the board. So we're still coupled to a larger machine to make these small models that run on hardware. And also, as we saw earlier, it can take quite a while to train, to kind of configure the models, to put them on the hardware. And so that's the kind of bottleneck in thinking about how we train models that use this sort of hardware. In terms of music and creative work, there's some challenges thinking about signal representation. So if we're using binary and logic gates, how do we represent sounds? And there's plenty of ways you can do that. You can use kind of binary pulses. You can use lots of different binary encoding schemes to think about how you can encode these numbers. And also thinking about tool chains and communities. So there's open source, which is happening at the moment, and I'll talk about this afternoon in the workshop, which is really promising. But these things are still quite hard to use and quite niche. And so if we're going to encourage people to use these creatively, we need to build a bit more of a community around it. So that's it. Thanks.
Questions?
Can you elaborate on possibilities of using machine learning in like sound synthesis? Like are you just making filters or oscillators, or how would you use this in like a synthesizer context?
Yeah, that's a good question. Well, I think there's a lot of the exciting thing for me in terms of wider AI at the moment is the work in generative models. And so where we kind of unsupervised train a model on a whole bunch of data and then get it to reproduce sound in the style of what we've shown it. So I think within that there's the Tama transfer model as well, where we can take these models and feed audio into them, and they'll kind of come out with something that sounds like what they've been trained at, but parallel to the input. And I think that's a really interesting thing we can think about, embedding these into musical instruments. So kind of having sound processors that can radically change the sound of how an instrument is sounding. And I've been trying this recently in the deep learning way, running in the GPU on my laptop, but feeding sounds into the instrument. But for me, thinking about how you can kind of make a self-contained instrument which has its own kind of machine learning process, its own data, own hardware, seems like an important thing to do to untether it from larger machines.
So as far as I understand, you are using mostly these small devices to run the neural network once it has been learning elsewhere.
Yeah.
So I'm trying to convince myself that there are applications where you would spend a lot of energy in training a network to put it on a very small device that's consuming so few energy. So what is a typical application that you're thinking of for this machine learning on music, for instance? Do you understand where I'm...
So you mean to kind of get away from, to move away from the kind of training and then...
Like if you're a musician, you put on your machine learning on a musical instrument, but do you mean that the musician will spend hours training an instrument for tuning his neural network, or will it be fixed once for all? Or?
Yeah, well, I think that's one of the research challenges we've got at the moment, that when we're using this sort of hardware, we're kind of tied up with bigger machines, and it'd be really nice creatively to be able to move the whole process embedded with the instrument. And I think that's important also in the way that when we creatively engage with machine learning, we've got this kind of split interface going on, that we've got this kind of very kind of scientific data science tools, and then we've got more creative musical tools. And if we can kind of try and merge those worlds into a kind of more continuous creative process, that would be a useful thing to do. Does that answer your question?
Yeah, but the time for learning is like very long, or is it? So you reduce the impact of the neural network, but is the time for learning reduced also, or it's even longer because we have small?
I see. Well, compared to kind of conventional approaches, I think the models I'm using, I mean, they can take quite a while to train.
Because you train on your simplified model. You don't train on the original model.
Oh, I see what you mean. So the approach that I'm taking with stochastic logic optimization, it isn't a tiny ML approach. So it's not kind of hacking down a deep learning model. It's building it from the ground up, but still it has to be built by simulating the logic gate network in Python. And then once you've built the model, you can export it into Verilog, and then you can run it on the FPGA much faster. So yeah, there's still that pipeline difference, which is a problem, I think. Okay.
I'm quite curious about audio gen. Have you been able to experiment with that? And is it really capable in terms of music creation?
I haven't experimented with much. I've just kind of looked through the examples on it. That's all.
Oh, that's for the laptop. It's okay. Perfect. Thanks.
Well, thank you, Chris. Yeah, I'm sorry we have to do these weird transitions, but there is a very specific setting to have for screens. If people online want to get the copy, we would just realize that. So it takes a bit of tweaking before it actually happens. But anyway, so now we have folks from Bella. And so we have Aiden here, and Clemens is here in the room. And yes. Well, did you lose your... it's loading.
Yeah, it's loading. Wow, okay. There you go.
There we go.
Hi, everyone. I'm Adan. I'm a PhD student at the Center for Digital Music at Queen Mary University of London, but I'm also one of the developers, maintainers of Bella. And I'm here together with Clemens. Oh, is it? Oh, shoot. Oh, okay. I thought it was too loud, but maybe not that much. So, yeah. Is that better? Okay. So today I'm going to talk a little bit about low latency interaction with Bella, the what, the why, and the how. If you've been to SMC, which happened here earlier this year, you recognize a few of the things that I'm going to show on screen. hopefully there will be a few that are new. And many of them, I'm sure most of you guys working with FPGAs will be really aware of. This is our particular approach. So who is Bella? Bella is now a spin-off company that was founded at the Augmented Instruments Lab, GRAME University of London, and is now affiliated to Imperial College as well. There's 5 maintainers, but since earlier this year, we joined forces for Bella 2.0 with the guys from CHAIR, from the Center of Haptic Audio. So Max, Clemens, and Sebastian. Clemens is here today, and he will be with us on the workshop. What do? We have this platform that I hope many of you are familiar with, which is an open source platform for creating interactive audio or interactive objects. We have several flavors and versions of the platform, but we have also worked on capacitive sensing just to try to make it more approachable for makers. And we are nerds, and so we like to put our things in Eurorack format. So we also have a few Eurorack things going on, a few of them at the moment. But yeah, what is Bella? Bella is an embedded computer designed for interactive audio, which is based on the now a little bit dated BeagleBone Black platform that has the power of a Linux single board computer, the connectivity of a microcontroller, and is optimized for real time. When we designed this, we took like a specific approach to high bandwidth sensor processing so that the analog digital inputs and outputs are sampled at audio rate. Which allows us to achieve really low latency, like below 1 millisecond. I mean, for FPGA guys, 1 millisecond is like, oh, like that's too much. But you can do interesting things. You can get to microsecond latency on Bella, and maybe perhaps as important, jitter-free alignment. So you can have the audio stream, the digital stream, and the sample stream sample line with almost zero jitter in most situations. And our platform is open source, and we are proud to develop a community around it, and we support it, and we use it in education. So that's part of what we do. Okay, interactive systems. Is this an interactive systems? Like there's some. I mean, this is a diagram of an audio process. You have an audio input, you get an audio output. You have your codecs, and the audio process can run on Bella. Where this is interactive or not, it's up to you. If you are controlling parameters, then perhaps it's interactive. If you are doing something based on whatever you're performing, then perhaps it's interactive. So it's something to take into account, and we'll see later why. But in many approaches, something that, like what we define in literature and across other people's works as an interactive system is something that has an action that is sensed, then it's processed, and then it controls the process that generates audio or manipulates audio, right? This, like, we try to make it really easy. This is our focus. Our focus is on making these things jitter-free, low latency, and actually approachable, which has not always been the case. Okay, so what is a real-time interactive system? Many people here know, but like there's this misconception. It's not a system that it runs really fast, but a system that does things without missing a deadline. There's a bounded time in which you need to do things, and a real-time system does things in that bounded time. It needs to be consistent, it needs to be guaranteed. As a general rule, in order to achieve this, the processing of each sample that you have in your input-output needs to take less or equal than the sample period average. If not, you will not be in bounded time anymore. And there's a differentiation between hard and soft real-time systems. We are talking about hard real-time systems here, the ones that never miss the deadline, no matter what happens. What is latency? There's been talks about latency today before. There's several definitions depending on how you're approaching it, but for an interactive system is the delay between an action and a reaction. The action being perhaps the input that you're gathering with your sensor, the reaction being the audio that you're generating. This latency latency is related to this upper bound that we define for the real-time system. So the latency of your system is going to determine what the upper bound is going to be, and the other way around. It's a mathematical property, so it doesn't matter how fast your system is, how parallelizable it is. This is something that you're going to have to deal with at some point. and it adds up. So you need to consider the worst case scenario. Like every bit of your system that has latency on it is going to add up to a greater latency. What are the latency deadlines that we find in interactive systems and in audio in general? This is a log scale for time, which is perhaps not the best way to represent time, but I thought it would be fitting for this presentation. About 100 milliseconds, you can actually differentiate different events as a delay, right? You can tell if your latency is greater than 100 milliseconds, then you can actually listen to events happening. In between 25 milliseconds and 100 milliseconds, you get this flanging effect, as some people miscalled back in the 70s, that is also perceptible as an audible as an audible effect. And then when you get below that, you perhaps don't notice it as something audible, but you start noticing it as part of your interaction. There was a study performed by one of my colleagues, by Robbie, he's also one of the developers at Bella, a while ago on setting different latencies for percussive instruments. And for example, like with 20 milliseconds, professional percussionists could already tell the difference in perceived instrument quality. This brings us to the 10 milliseconds upper bound, which David Wessel said in 2002, and is cited all along NIME, and is used as a measure of how reactive your system is. But even below that, latency can be important, right? So this tells you that 10 milliseconds should be the ideal aim for an audible reaction to gesture. But below that, you have other things. You have USB MIDI, for example, can take 5 to 6 seconds. So whatever you do needs to be done between those 5 to 6 milliseconds, sorry. If you're doing active feedback control, you probably want sub-millisecond latency. Even more if you're doing traveling wave estimation, that's active feedback control in which you're actually trying to predict where the wave is, you want that latency. But moreover, what I would like people to take away from this, and many of you might know already, you always need to consider the worst case performance. So wherever you can reduce latency, do it, because then you might have to increase it for a later process somewhere else. And as I said, like performers don't want their instruments failing. When you're creating music, you want to be engaged. Anything that is disruptive is going to mess with that performance. So you want to create systems that are hard real time, that meet the deadlines every time. Okay. Okay. What happens when latency changes over time? There's this when you're on a round trip audio latency, or kind of like a processing latency situation, latency tends to be constant. You tend to have the same consistent audio latency, right? But whenever you're trying to interact with that audio stream and you have things that happen in a different thread, in a different process, then you can introduce this effect that is the random variation of latency called jitter. That happens a lot when you treat sensors as a different thread. So let's say you have different blocks that you're reading from audio, and then at some point you receive a trigger from sensor data. If this is in a different thread, the sooner that you can react for this is going to be the next lock. And same. So you're going to have this perceived misalignment of your action and the sound that you're generating, which is what the jitter, what jitter means. And this increases with block size. If your block size is bigger because you're trying to do some bigger processing, jitter is going to increase with it. This has proven to be, if not as disruptive as latency, more disruptive. So again, David Wessel's wisdom tried to achieve 1 millisecond jitter as the maximum of your system. But if you have 0 jitter, that's even better. 3 milliseconds jitter for professional percussionists has proven to be even worse than like a double increase in latency from 10 milliseconds to 20 milliseconds. So something to take into account. Okay. What are the sources of latency in the system, right? You have, this is an audio system, you're reading some inputs, then you have your analog realm where the audio exists, then that's converted to digital bit stream, sorry, that's processed by some drivers, and then you have some processing code, which is usually the part where you write and do interesting stuff with it. You have the conversion latency from analog to digital and digital to analog, which is, as it has been mentioned before, is inherent to the code, to the codecs that you use for that. So you can get up to 500 microseconds. As I said, it doesn't sound too much, but everything adds up. And maybe extra if you're using other kind of converters. You have the buffering latency. And this is a function of your architecture. It depends on how your block size is handled and the size of your block size. This tends to be quite substantial, especially if you want to do things that take more than just a few samples. And then you have the group delay, or the latency that your audio code takes, right? Where that's filters, where that's block-based processing like FFTs. Everything has this code that you're going to write is going to have an inherent mathematical latency, as it was shown before with the filters. What can you do to solve these bits? For the conversion latency, you can try to use a higher quality ADC or a codec, or one that doesn't use filtering, as we do on the analog inputs on Bella. For the buffering latency, it's up to how you really structure those buffers. It's up to the OS and the buffer size that you use. And for the group delay, it depends on your code. It really depends on what you're writing, what you're trying to achieve there. The problem gets even worse when we are trying about interaction and trying to use data from sensors to manipulate audio. This is what many people do and how many interactive system design classes are taught. You have a microcontroller that gathers some sensor data, transfers it over serial to a computer, and you react to that sensor data. There's a few problems with latency with that. You have the sampling latency of the sensors, which can be something between 1 to 100 milliseconds, depending on which sensors you're using, and the protocols that those sensors communicate with the microcontroller with. You have the communication latency. These numbers are a little bit dated, but you'll be surprised that many people still use 9,600 bits per second in their code, but it adds up. If you're communicating over a wireless protocol, this is going to increase. If you have a better protocol, this might decrease. Is there a better protocol than USB? I mean, USB has improved a little bit, but still. Then you're going to have the OS driver latency. Most drivers in a normal OS are not tailored for speed. You need a specific OS that does that, and it's unpredictable. It can be really good until once it's really bad, and then it screws everything up. It depends on what processes are running on your operating system. And of course, you have your audio latency. What can you do to solve them? I mean, you can use different sensors, you can use different standards for communication, or you can have custom drivers. Or you can just not have any communication, or you can just figure a different protocol. What do we do with Bella? I'll get into that a little bit later. Okay, I'm not gonna get, since we are constraining time, I'm not gonna get into this because I assume that many people here know how buffering and latency latency works. But when we gather samples from a buffer, we cannot immediately use them. We need to be able to process them and then feed them back to the output. So you usually end up with a couple of blocks at least of processing latency. So that's something to take into account. If you have a block size of 16 samples, then your latency is going to be 2 by 16 divided by your sample rate, obviously. And at a given time, your system is going to have to be gathering data, processing data, and writing data to the output. But what happens when you want to run processes that take longer than 16 samples, 256 samples? That could be an FFT, that could be some machine learning prediction, that can be granular synthesis. How do you deal with that? We usually use overlap and add is one of the methods that is used, on which you gather windows, you overlap these windows, you add them, you do whatever processing needs to be done, and then you add them together at the output. In the FFT is one of those cases. And the important thing about this is that it's non-causal. Any block in your output is going to depend on future blocks in your input. So that's going to add latency. Even if you had an ideal system with no conversion latency, not buffering latency, not communications latency, if you want to do block-based processing, that's going to have inherent latency. So yeah, in the case of EFFT, you get a block size a block of size m by window, you perform the FFT of it, you do something interesting with it, you perform the FFT, add a segment to output buffer so that you can write it back, and then when you write it back, you advance by the hop size. As I said, ideally you would want to have a block at your input and immediately write the block at your output. But in reality, that doesn't happen, right? It's non-causal. You need information from the future, so you need to wait until that information is filled. It's a non-causal system. So what's the best that you can do? The best that you can do is wait by the size of the window of the process that you're trying to run, right? What happens then? You solve the problem, you have the data that you needed, but then you only have one sample to process it. How much can you do in one sample? That really depends on how your architecture is scheduled, but is organized, but usually not much. So at least you need to wait for the next hop size to be able to do the computations for the next window. So even if you had that ideal system with no latency at the input, no latency at the output, no buffering latency, and you're doing some block processing, you're going to have an n+h latency, inherent latency in your code. This is important for the kind of stuff that the people, for the trends and the kind of like the more computationally expensive trends that are taking these days. You usually need more time than what your processor is capable of doing unless you have a massively parallel processor to do the things that you want to do at the output. It also has an effect on jitter. If you, let's say you're reacting to events that come at a specific point, that could be percussive events, or that could be data from your sensor, you're quantized by the hop size. And this can have several issues. How do we do this in Bella? Bella has an audio codec and a DAC and an ADC that use communication interfaces that could be implemented in Linux. But why don't we use Linux? Linux and ALSA can handle multimodal stream and also don't offer strict timing guarantees. The way we solve this is by using a responsive operating system based on Xenomai, on which the threads run when we want them to run as often as possible, and a sophisticated DMA memory access controller based on the PRU, on which the audio analog and GPIO are aligned at audio rate. The Xenomai system, I can get a little bit into detail. I'm running out of time, so I can get into detail later. But it makes the audio thread run at higher priority. Nothing messes with the audio thread. You can run other Linux processes if you want, but the audio thread takes priority over anything else. I'm not going to explain this. But I'm going to get a little bit into why don't we just use Xenomai. If you wanted, you could write a hardware peripheral a driver for the hardware peripheral for Xenomai that does it, but Xenomai doesn't really work at sample level, so you will miss that alignment of audio, digital, and analog. And also, you will need a dedicated core. When we implemented this, we only had this single core device, so it was not really an option for us. What did we use instead? The nice thing about the Citara socks that we are using is that it comes with a programmable real-time unit that is optimized for time-sensitive tasks and runs really fast instructions, and shares memory, has its own memory and shares the memory also with the CPU, and can generate and receive interrupts. So what the DMA does, the DMA controller does that we wrote on the PRU, it basically takes your audio input, takes your audio output, takes the analog ADCs, takes the digital I/O, and in as fast as possible, if possible in half a block size, mashes all them together in a sample aligned buffer that then you can use. So whenever you're starting to write your code, you have a buffer that is sample aligned for audio, digital, and analog. That allows us to use sensors as audio, so that you get rid of that jitter. It's almost a zero jitter system. There's sort of figures of the kind of latency that you can achieve with Bella. You can achieve under millisecond latency have some people have done it. You basically need to use need to get rid of the codec and use the analog inputs and outputs. That's where you see that everything really adds up on the system. If you use a sigma delta codec that has some filtering on it, that's gonna add up to the latency of your system. Okay. Apart from that, why do we use a Linux computer instead of a microcontroller? It allows us to do these kind of things. It allows us to really easily have different kind of languages running on it. We don't need to write compilers. We don't need to mess up with it so much because we have already a Linux machine that is able to compile code for us. And moreover, it allows us to have a pipeline that is integrated in our system. In our case, and if you come to the workshop later, you'll see it, you don't need to install any drivers usually. You don't need to install any pipeline. You can just hook up the board to your computer and compile it and run it. Yeah, if you want to learn more about Bella, it's open source. It's a project that's always open to contributions. We have a knowledge base with lots of information, a forum where Julio is usually giving answers to people when they want them. We have a blog where we showcase the things that we do. And there's a YouTube course on real-time processing with Bella, which is freely available. And since you had to listen to me for 20 minutes, I'm giving you a 10% discount on kits to the end of the month, in case you thought that Bella is an option for you. Thank you very much. And yeah, any questions?
Do you have the name of the audio codec that you? I suppose you use an audio codec to do the conversion. Yeah.
It's a TI-TLV. I don't remember, but I don't
just the brand. Do you know the?
It's TI, Texas Instruments.
Okay.
Yeah.
Right.
That's for the audio codec for the ADCs and the DACs. We actually, like the ones that are there, we actually are changing them for a new revision because of the semiconductor crisis. Yay! So yeah.
Okay. Yeah. Yeah, because you know the latency that just the audio codec add to your system, or?
I don't remember how much is the group delay. How much is the filtering delay of the signal delta converter? But I think it's about I think it's around the 500 microseconds.
Okay.
Deadline that I put in there. Yeah.
Okay. Thank you.
But yeah, I can check it on the datasheet later. Yeah.
Other questions?
Thank you for the presentation. I would like to also ask, you said also we could bypass the codec somehow. I didn't really understand how.
I mean, it's not that you can bypass the codec. You can just use the analog converters instead of the audio codec. That means that you're gonna have DC couple audio, so you're gonna have to decouple it. And of course, it's not a signal delta converter, so the quality might drop a little bit. So the converters that we use for the analog. They are successive approximation register converters. That means that they don't have the filtering that you will have on a signal converter, so they are faster. Actually, I need to check how much it is, but they are faster. But the problem is that they are a little bit noisier. I mean, signal delta converters were designed to deal with that noise that the successive approximation register converters don't have. But people have used them successfully, for example, like for feedback control.
Great.
Yeah.
I don't think we have any questions online, right? Okay. Well, thank you. Tommy? Mirror display. Okay. Oh, mirror. Okay, but then. Oh, it's like it thinks that this screen is your computer screen for some reason. So, display.
I'm expecting to see.
Well, also like the configuration is not good for streaming, so. Display. Okay. On voit pas son écran. Lui, il voit rien. Non.
Yes, I can try and maybe borrow Stefan's computer.
Maybe Stefan? Yeah, maybe.
Try.
Yeah.
Thank you, Stefan.
Tu peux vérifier? Ouais, c'est bon. Donc là, ça marche.
Alors, ça, c'est ça.
Ok. Are you playing audio or no? Okay.
You have a PDF, yes?
Oh, no.
Yeah, a keynote. Okay.
Do I get a speaker? That's just the question.
Faut vérifier. 3. Okay, nickel. Okay, great. Maybe you want to wear this. Okay, so this is the last presentation for this morning. It's going to be given by Thomas Rushton on microcontroller-based network client towards distributed spatial audio.
Thanks very much, Roman, and thank you all for having me. Great honor to be here in such a esteemed company. So, my name is Thomas Rushton. I've been working with the Emerald team based here. I'm a second year master's student, I'm on an internship here, but I'm a student at Aalborg University in Copenhagen at the moment. So, what have I been working on? Network distributed spatial audio, essentially. So there's been recent interest, I guess, past couple of decades, especially in immersive audio experiences, VR, AR, sound spatialization, that sort of thing. Certain techniques, ambisonics and WFS is one that I've focused on. These call for large numbers of speakers, consequently, specialist hardware, powerful systems, centralized, and probably in situ, not mobile or flexible, really, to speak of. So what if we could create an alternative, something that is flexible, that's scalable, it's adaptable to other purposes, it's maybe it makes use of distributed computation, maybe it's low cost even. There we go. Okay, so focusing on WFS as I did, I think it's useful to give a little background just to start off. So what is WFS? So it's essentially it's a form of, to give it its grandiose description, acoustic holography. That's how Burkhout put it in his paper from 1988. So the dotted lines here in the diagram indicate sort of per speaker delay lines, or rather the control data that's used to describe those delay lines, or from which those are derived. Ultimately, like in working out what the delay lines should be, we can throw away, this is an XY coordinate system, we can throw away the Y coordinate for the length of the delay lines and just keep it for doing things like simulating the changing gain with simulated distance from the speaker array, and also for the, say, low-pass filtering, since high frequencies will be lost more readily to the air, the medium of transmission. What this indicates, though, is that in order to create these stimulated wave fronts here, the blue lines, there needs to be a good deal of synchronicity between the speakers in the speaker array. And this sort of system is going to need a lot of audio I/O. Each virtual sound source is going to be a distinct channel of audio, and the WFS algorithm is somehow going to have to be connected to a lot of distinct speakers. So that comes back to what I was saying before about a centralized system. So, oh, sorry, I forgot to advance my slides. So what if we could turn that into something like this, where we've broken down this monolithic algorithm into something that's distributed. So each of these distributed instances still needs to know where each of the sources is. It also needs to know which speakers it's in charge of, but it only needs to produce output for in this case, 2 of those speakers at a time. So this brings us on to the topic of networked audio. What is networked audio? What's it being used for? So we had a great talk on Jack Trip earlier on from Nando, and so that has, particularly during the pandemic, supported things like remote rehearsals. It also supports large-scale professional live audio systems. And what platforms, protocols exist to support networked audio? Well, there's Jack Trip, as we heard. There's the Jack audio connection system contains the NetJack protocol. There's Jamulus, which is another popular jamming platform during the pandemic. There's Dante, which I think is a proprietary system. That's a sort of one that comes up in professional large-scale applications. So why not just send audio? Why send as audio over sort of traditional audio cables? Why send it as network information? Well, the distributed case I was hinting at a moment ago, say each of those individual modules only has a limited number of I/O channels, but we want to support a large-scale system like WFS. We may be able to send more channels over a network than we could simply using regular audio channels. So what are the limitations? Okay, well there's the size of the datagrams that we can send over our network protocol. In terms of the UDP protocol, which is something that Jack Trip, for example, is a layer on top of, the maximum datagram size is 64 kilobytes. But in practice, this is limited further by the maximum frame size, the MTU of the underlying protocol. In this case, it's going to be Ethernet, and that's going to be around 1,500 bytes, but that's going to be hardware specific. In addition, there's things like default socket sizes on your hardware. There's also how server software has been structured. Can we send data over UDP multicast, for example? And is there some kind of threading model in the server software, for instance? Okay, so taking this idea on and thinking, okay, so how can we use networked audio to create a distributed WFS system? Let's look at the hardware that we employed. So we used a TNC 4.1, or rather several TNC 4.1s. And so this is the small collection of objects from which our modules are constructed. There's a TNC 4.1 here. It's got an audio shield and built-in Ethernet functionality. For a microcontroller, I would say it's pretty powerful. So it's got a pretty solid CPU, a good amount of RAM. It supports audio buffer sizes, well, modifiable audio buffer sizes. I found it could run down to about 16 samples reliably. There's no OS, there are no threads. It's a double-edged sword. That being the case, everything runs on hardware interrupts, essentially. And so this has ramifications for timing. It's pretty good in terms of its timing, but in terms of implementing sophisticated processes, it can be somewhat limited. As the name suggests, it's pretty small TNC. It's about 6 centimeters in length. And it's affordable. It comes in at about 30 euros. So let's now look at the kind of how the system was developed, the audio server for a start. So to the left we have Jack, the recursive acronym Jack Audio Connection Kit, and this is an inter-application routing system for audio and MIDI. And then there's the Jack Trip protocol, which uses as its backend Jack as its audio server. So this is the command for starting Jack Trip as in hub server mode. So the capital S is hub server. Q is the packet buffer length that Jack Trip will use. And P is an auto-patching mode, so whether any clients that connect to it should be connected to each other, connected to themselves. The number 5 says no auto-patching. Patching can subsequently be done using Jack's API for connecting ports. Any client that connects to a hub server, as long as it sort of does so in the correct way, will appear in Jack, in the routing graph, as an audio device with a number of I/O ports specified by N here, the final argument to the hub server. Okay, so one of the attractions of using Jack Trip for this was its comparative simplicity as a protocol. To get a client to communicate with Jack Trip and start exchanging audio as encoded as UDP data, so 8-bit words, is to start by sending a handshake over TCP. So the client says, hey there, Jack Trip, here's my UDP port. Jack Trip goes, cool, I'll start a send and a receive thread for you. And, well, it doesn't tell it that, but that's what it does in the background. What it does tell the client is, here's a UDP port that you can reach me on. And that's kind of it, really. From there on, the server and client just have to maintain this flow of UDP packets, send and receive, essentially. And that can continue ad infinitum. So, I mean, the client could be another Jack Trip process running on the same machine. It could be a remote machine that knows the appropriate IP. It could, in our case, be a microcontroller that, again, knows the correct IP and initiates this handshake and then starts exchanging, audio in UDP packets. As long as the client keeps sending those packets with the correct structure, the correct headers, it'll stay connected. And yeah, the only condition is on this packet structure here. So what I found was timestamp and sequence number actually kind of don't matter. I mean, they could be helpful in terms of diagnosing things like synchronicity, but the things that do matter are the sampling rates have to match. And Nando may correct me on this, but buffer sizes have to match as well. Otherwise, I mean, particularly for the client, as we implemented it, the buffer sizes have to match. Otherwise, you get malformed packets. It's difficult to decode those into audio data. Okay. So from there, we can deal with multiple clients. Each of these makes that TCP handshake, initiates a flow of UDP audio data. But here it's informative to make a distinction, I think, between what's happening in terms of network communication on the one hand and audio routing on the other. And so that looks like this. Clients are connected to the server and they're exchanging UDP packets as described. And what we can have is an audio application that's not necessarily a jack trip client. It's just something that exists within the jack audio routing system. It's sending, that can, via that system, send audio to the jack trip clients. And this can be, as I'm illustrating here, multiple channels of audio. So here's kind of an architectural overview of our system. So now, and I thought my diagrams were going to get quite convoluted and difficult to follow. And then I saw Nando's, which were very impressive. But yeah, so now the initial system is fading as the background. We have this main overview. Our audio application is sending audio over UDP into the Teensy audio library. It's being received by this jack trip client, sent to a WFS algorithm, which is going to Teensy's outputs. And the client can also send audio back to itself that then gets sent back into jack over UDP. In turn, the WFS algorithm, which was implemented in Faust, consists of taking the incoming audio sources and creating this kind of, let's see, for the speakers that the Faust algorithm knows that it's in charge of, it creates this, how can I put it, this view of the virtual sound field, basically, and then sends it to its two output audio channels of the Teensy. And then additionally, we've got this WFS controller, so that is sending audio essentially to jack, that jack trip is then handling over UDP. It's also sending control data in the form of OSC messages. And these are actually being multicast to all the clients that are connected at that point in time. So there's a particular address range that's, let's see, reserved for UDP multicast. And so the Teensies are all subscribed to the appropriate multicast address, and the application is sending control data. So it's telling each client where it is and which speakers it's in charge of. It's also telling each client where the sources are, and then the Faust algorithm does the rest. So what are the challenges here? Okay. The big one is clock drift, temporal inconsistency. So what I found is that Teensy's timing is pretty good, really good in fact. So the interval that it's reporting between audio buffer increments is really steady. I think at a 16 sample buffer, it's something like 363 microseconds, and that's, yeah, it's the average time reported by Teensy stays very close to that average. The server and network, less reliable in this regard. So yeah, the rate of UDP transmission does not equal the audio clock for anything. So this requires compensating for the fact that during a given hardware interrupt on Teensy, when it's hoping to receive a UDP packet that it can use for audio purposes, there's probably going to be one available, but there might not be. And then the next time there may be two, and so on and so on. here's a little sort of debugging view that I used. So this line here shows, and this was for a 32 sample buffer, the minimum and maximum don't stray too far from the mean for the receive side, so it's teensy, sorry, for send for the teensy, and then receiving from the server, there's a much bigger variance here. So how can we compensate for this? Essentially, the approach is that I employed was to treat the server and UDP input as authoritative, even though, as I've just described, the server is pretty unreliable timing-wise, but it's the source of the audio, so it has to be treated as authoritative in this case. And then, so receiving the audio samples, writing them to a circular buffer, and then by a process of adaptive resampling, compensating for the fact that, there's drift in terms of the read and write positions to that circular buffer. So, as best as possible, keeping the read position about one buffer behind the write position. This involved employing a fractional read buffer index, adjusting that position relative to the delta between the read and write positions, interpolating and smoothing, and ultimately, and I say this not meaning to be too facetious, but keeping fingers crossed and kind of hoping for the best. So that being said, how does this perform? So with a block size as low as 16 samples, things were running pretty stably. I tried down to 8, and that was about the limit. 16 works stably enough, 8, and things didn't seem to kind of hold together. The FPGA people in the room are going to hate me for saying this, but latency, 1 to 10 milliseconds. This is dependent on what block sizes are being used. This is in terms of measuring output from the server as UDP, and then being sent out by the client as audio, and then sent to another machine to record it. So there's latency at a bunch of steps here, including the input on whatever audio interface is being used to make the recording. So the true latency from the server over UDP to the teensy and then as audio output is certainly less than 10 milliseconds. It's pretty low. More importantly though, the synchronization it's quite good. The clients are synchronized to within about one buffer. And so that's with the proviso that there are occasional glitches. The system as implemented could be certainly refined in terms of refining that, synchronicity between the server and clients. So just to illustrate, so this is sending a low frequency square wave that you can see at the top from the server to some clients, and then back into an analog input on a sound card. So obviously the ADC there has smashed this square wave to bits. But you can see that the latency there is around, actually you can't see the numbers here, but the latency from the server to the clients and back to the audio interface, it's about 7 milliseconds here. But what we see is that between the two clients pictured here, the offset it's a handful of samples. We're in the sort of 20 sample sort of range here. And this is running with 8 clients. And so the spread here is, this was running at a buffer size of 32, and the spread it's high 20s somewhere. You can see the individual sample points. And the offsets do vary over time because each client is adjusting itself relative to what it's receiving from the server. But so although the offsets drift, they do so within this range of, let's say, 20 to 30 samples for a block size of 32. So let's see, there's more that could be done here. For one thing, the system is designed assumes a local network, but this platform, the Jacktrip client on a microcontroller, could be used for things like, as described earlier, for remote rehearsals or creative installations, these sorts of things. There are other spatialization techniques, ambisonics, for example. Better synchronization could be possible via multicast. Multicast is not supported by the Jacktrip protocol. NetJack does support multicast, but it's a more sophisticated protocol in some ways to interact with. It's something that we began to pursue, but ultimately it's sort of escaped the scope of this project. But yeah, certainly something for future work. Alternatively, there's using an external clock, but that starts to make the system less accessible, less useful for maybe packaging up and having as a self-contained device. Plus something like precision time protocol would require specialist hardware again, so that defeats the initial purpose of making things sort of accessible, flexible, and so on. There's alternatively options like maybe trying to tweak TNC's clock on the fly, adjusting its PLL, but having experimented with that, I imagine it's possible, but for the kind of application that we were trying here, I found it to be pretty, unstable, difficult to manage. And also, it would be interesting to try and implement something in a truly distributed fashion, so something without the centralized server, or perhaps a server running on a more sophisticated single board or microcontroller, something that maybe runs an OS or has threads. But yeah, it would be nice to try implementing as much as is required to run a server on the TNC environment. So you could have one microcontroller as a server and a bunch that would then connect as clients, for example. Okay. Anyway, thank you very much, and I welcome your questions. I also will be demonstrating the system as it stands upstairs this afternoon. So yeah, thank you very much.
Questions? Maybe you guys are hungry. I can't really ask questions because I was Tommy's advisor for this project. So I feel, but
I mean, you could if you wanted.
I think I know the answer. So. Oh yeah, Nando.
Yeah, have you? Very interesting.
Thanks.
Have you considered other protocols other than Jacktrip?
Yeah, as I hope I just alluded to.
Some.
Yeah, NetJack was one that we looked into. I mean, Stefan, you were instrumental in the development of NetJack, and we think it should be possible. But the way that NetJack is structured, I started trying to unpick it, but it's just going to take me or someone else more time to do so, to create a kind of reduced client implementation. Like as I said, Jacktrip has this massive advantage of being so lightweight in terms of making that initial connection and getting things going. Yeah, NetJack, sorry, it assumes the availability of a threading model, essentially, a native threading model.
You may consider also creating your own non-protocol, which would be just sending raw data.
Yeah, I mean
recovering the clock from the data arrival.
Yeah, I mean, you'll forgive me, but that sounds like that's how protocols are born, isn't it? I think. I mean, yeah.
We don't have enough, right?
No, indeed. But yeah, I mean, that idea crossed my mind. That would be a way to go, kind of. Particularly if everything was contained to the microcontrollers, then yeah, a dedicated TNC Jack protocol of some kind would be.
I did something similar
Yeah.
a long time ago. So we should talk.
Yeah, we should.
Yeah.
That would be great. Thanks, Nando.
Other questions? Okay, well, thank you, Tommy. So before you guys all run away to get food, because I know that's what you want now, I just want to give you a couple information. So first, we will resume at 2:30, okay? As I told you earlier, and as Tommy actually reminded you, there's a bunch of installations upstairs. There are 3 of them, okay? So Tommy's system is being demonstrated upstairs. We have an FPGA-based WFS system, which is also being demonstrated. And also there's the SPAT box by Pierre Lecomte. Pierre Lecomte is going to give a presentation on the SPAT box at 2:30, but you can already go try it from 2, okay? So you're probably all going to go for lunch, but at 2, we'll all be there if you want to check those systems up. I'm saying that now because there is going to be a coffee break in the afternoon, but then there is going to be very limited amount of time after the conference to go check those things. So it's probably better if you go do it at 2 or something like that, you know, like or before we resume. There will be time during coffee break in the afternoon as well, but you know, it's probably better like that we sort of split for this. Okay, so those of you who gave a presentation this morning or who are giving a presentation in the afternoon, you're gonna get lunch with us. Okay, so it's gonna happen here on site, you know, and we have your lunch covered. People who are not presenting, yeah, there's nothing open on campus for food during the weekend, okay? So we'll resume at 2:30. Thank you. Okay, one last thing. If you want to leave your stuff here so that you don't have to carry your stuff with you, you can put everything in the blue room, like in the back of the theater. Over here, we're gonna lock it, okay? So if you want to leave your stuff, you can leave your stuff there. We're gonna lock it, and if you need me to open the room later, just find me. I'm gonna be around. So, yeah.